Hello everyone, my name is Samat Koita. Today I will be presenting our work on real-time video-based fall detection using long short-term memory networks. This project is a collaboration between Mohammad Tawfiq and Samat Koita from the Indian Institute of Technology Bombay and Nikolai Spiker and Professor Thomas DeSerno from the Peter L. Reichardt Institute for Medical Informatics. In this paper, we work on fall detection systems. Falls are a major health risk for elderly people. What makes it worse is that immediately after a fall, elderly people, especially those who live alone, are unable to call for help on time. Identifying falls and sending alarms as soon as possible can often significantly reduce negative consequences for these people. That is where fall detection systems come in. Some common methods for fall detection include using wearable technologies and sensors, using 3D depth sensing cameras, etc. However, these methods are often invasive and involve having the person wearing something, inaccessible, or expensive. Rapid improvements in the field of computer vision have led to a surge in popularity of video-based fall detection methods. This is what a video-based fall detection system looks like. Input to the system is a video feed, and the system detects in real time whether a fall has occurred or not. In this work, we make use of latest development in computer vision and machine learning to propose a new methodology for multi-person, multi-camera fall detection. Prior work on fall detection can be further divided into three categories. First, we have classical signal-based methods. Classical methods look at indicators from the video frames. For example, angle of the person from the vertical, rate of change of height of the person in the video, and predict whether a fall occurs or not based on some pre-decided conditions. This has certain obvious limitations. It simplifies the problem too much. Real falls are much more complicated and cannot be reduced to simply checking whether some features are below or above a particular threshold. Next, we have classical machine learning based methods. ML based methods extract features similar to the classical signal based approaches. However, instead of having a pre-decided condition, these features are used to train a machine learning classifier, which predicts whether a fall has occurred or not. Algorithms such as random forests, logistic regression, etc. are commonly used. The limitation of these approaches is that the features used, for example, bounding ellipse of the person, rate of change of height of the person, do not capture enough information about the person to predict whether a fall has occurred or not accurately. In addition to this, they are not well suited to handle temporal data across multiple frames. Of late, end-to-end deep learning methods have gained popularity. They are based on neural networks. These neural networks take a sequence of frames from the video as an input and predict that a fall has occurred in the sequence or not. These neural networks are trained on fall detection datasets. The problem here is that due to the end-to-end nature of this approach, the performance is highly sensitive to the quality of the dataset. Videos of falls occurring in the real world are quite difficult to obtain. Therefore, fall detection datasets contain videos that are filmed in lab environment by researchers instead of real falls. All the videos created are in a similar environment. This lack of variation in the dataset leads to overfitting and poor performance of these end-to-end models in real-world settings. In this paper, we aim to overcome these drawbacks and propose a new method for real-time fall detection. Here is a demonstration of our system. Certain key points and features used by our system has been highlighted. Above every frame, we display the prediction of that particular frame, whether it is fall or not. This is a rough schematic of our approach. We will explain each step in detail further down in the presentation. Before we start, we attach multiple cameras to our system. Video feed from each of these cameras is used as input to our system. The first step of our method is human pose estimation. Human pose estimation algorithms take video frames as input. For each person in the frame, they assign a set of key points which represent the coordinates of various body parts such as head, neck, hands, legs, etc. These key points are used in later stages for feature extraction. The advantage of using human pose estimation compared to, say, traditional ML or end-to-end deep learning models is that one, they give us very accurate estimates of the exact pose of the person, which very often is enough to determine whether a fall has occurred or not. Second, the features that are obtained using key points can be interpreted by humans. This is quite useful in the later stages of processing. Third, these methods work even if part of the view of the person is obstructed and if there are multiple people in the image. For example, in the figure on the left, not only are there multiple people, but if we observe closely, the foot of the person who is standing can be identified by the algorithm even though it is blocked by another person. Once we have the key points from the video of each camera, our next task is to map key points of the same person obtained from different cameras to each other. This is a demo of our people tracking system. People who are identified in both cameras are given the same color. As you can see, the skeleton of the person in the gray shirt is pink in both frames. This shows that his key points from camera 1 have been successfully mapped to his key points in camera 2. The next stage is feature extraction. We use the key points obtained in the previous stage to extract meaningful features that are used in the later stages for the final prediction. For each person, a separate set of features is extracted for each camera in which he is present. Some important considerations for choosing features are: first, stability of features. Small inaccuracies and a few missing data points should not have a drastic effect on the result. Temporal continuity of features should be maintained throughout the sequence of frames. Next, we should ensure that our features correctly account for the temporal relations between frames. Though features correspond to a single frame, they should capture the movement of the person across different frames. Next, we talk about feature selection. Features were selected based on analyzing the raw key point data, getting ideas from concepts of physics, as well as studying the features that were used in previous work. To capture the complete motion of the person, we extract features corresponding to the position, velocity, as well as acceleration. For example, corresponding to position, we use the angle of the person's body with the vertical, shown as θ2 in the figure. Corresponding to velocity, we show the rate of change in θ2, or the angular speed of the person. Now that we have extracted features from the video frame, our next goal is to predict whether a fall has occurred or not. We represent fall detection as a supervised learning task. At a given time step t, we use the features extracted from all previous time step till that time step as input to a machine learning classifier. The classifier then predicts whether a fall has taken place in the current frame or not. During training, we compare the output with a true label for the current frame and update the model parameters accordingly. We use an LSTM, long short-term memory neural network, as our classifier. Our motivation for doing this is because LSTMs are very well suited to handle sequential data. Here is the rollout diagram for our model. An LSTM has certain internal parameters shown here as HI and HI prime that represent the current state of the network. At time step t, using the input features xt as well as the current state, the network predicts whether a fall has occurred or not. Accordingly, it also updates its hidden state and is now ready to receive input for time step t plus 1. Now I'll talk about the data set that we have used. We use the UP fall detection dataset to train our model. It contains videos of different test subjects performing different actions. Actions include 5 types of falls, such as falling straight, falling backwards, as well as common day-to-day actions, such as standing, jumping, bending, etc. Each frame of the video is labeled by the action performed in that frame. We use a 5-fold cross-validation to evaluate the performance of our model. Here are the results from our experiments. Accuracy and other metrics are calculated by comparing our prediction for each frame in the video with the true label of that frame in the test set. We went through several combinations of neural network architectures and feature subsets. We found that an LSTM network with all 5 features outperforms all other algorithms, such as logistic regression, random forest, as well as LSTM with different feature set. The final stage of our approach is a post-processing stage to detect false positives. Before we get into details, let us understand why this post-processing stage is required. One of the biggest hurdles for vision-based techniques is the lack of good quality data sets. Videos of falls are difficult to obtain, and therefore, instead of natural falls, fall detection data sets contain videos of people enacting falls in a lab environment. A consequence of this is that fall detection data sets do not accurately represent real-world scenarios. Falls present in the data set lack variation in terms of the posture of people while they are falling, as well as the angle from which the fall is captured. The second problem is that of false positives. Fall detection datasets do not contain enough examples of people performing actions that are similar to false but not false. These actions are likely to be incorrectly identified as false by any vision-based methods. In addition to this, the training data must contain a significant percentage of false, whereas in reality, falls are much less frequent. In order to decrease the number of false positives, we perform some additional checks and balances whenever the LSTM classifier predicts a fall. For example, we notice that a fall lasts for approximately 1 second, which is around 15 to 20 frames. Most predictions that lasted fewer frames, for example, between 5 to 10, were found to be false positives. Therefore, whenever a fall is predicted, we first check whether the predictions of the previous 9 frames were also false. Only then do we claim that a fall is detected. Similarly, we check whether the angle of the person's body from the vertical is greater than 45 degrees and at least one camera, and that the distance of the person from the ground in the current frame is less than the standing height of the person by a factor of at least 2/3. We found that these methods decrease the number of false positives significantly. The number of videos in which the false positives went down from 33% to 9%. However, the number of videos in which a fall occurred but was not detected went up. Overall, the accuracy showed an improvement. Now I'm going to talk about the key contributions of our work. We propose a new methodology for multi-person, multi-camera fall detection. As a proof of concept, we implemented an open source application, link given below. We improved on existing state-of-the-art methods by using human pose detection along with the state-of-art learning methods for fall detection. In addition to this, our system supports identifying and tracking different subjects across multiple cameras. Lastly, we have ensured that the system is efficient enough to run on devices with low computing power and does not have a strict GPU requirement. This reduces the running cost of our system. To the best of our knowledge, this is the first open source tool having the following features. Here is a demo of our system. It is important to note that the video shown here is from a different data set than the one that was used for training, and hence is a more accurate representation of real-world settings. As you can see, our system is depicting that the subject is in normal state right now. Once the subject falls, we can see that the system has detected a fall and it is lasting for multiple frames. With this, I end our presentation. Thank you everyone for listening. In case you have any other questions, feel free to contact us. Our email IDs are given in the slide below. In case you wish to learn more about our work, please read our paper and visit the GitHub repository. Link to the GitHub repository is present on the previous slide. Thank you once again.
Hello and welcome. I'm Tim Wesemeyer, currently enrolled at Technical University Braunschweig, and I want to show you some of our findings in the next couple of minutes. Medical image segmentation with deep learning approaches is a common task nowadays that needs large amounts of data in form of annotations. So how do we obtain those annotations? One promising solution is crowdsourcing. While this is a good solution, there are open questions like, in which way do I want to collect the annotations? In which way should the user annotations be distributed among the images? So, in this work, we propose an approach for collecting annotations using crowdsourcing more efficiently. Previous work showed that you can combine user annotations to reliable ground truths using the staple algorithm. This ground truth is on a level with the preferred gold standard manual expert segmentations and can generalize better on unseen data. This is leading us to our research questions A and B. How does the quality of the annotations influence segmentation results of the neural network? And B, can we compensate the lack of high quality annotations for few images with low quality annotations on more images? Or briefly summarized, which quality of annotations is needed for training, and how do you distribute those annotations on different images? Let me start with our datasets collected from previous studies. We have a high quality but low quantity dataset, including 75 images, over 2000 annotations, and at least 24 annotations per image. And we have a higher quantity but lower quality dataset B with over 900 images, 2,700 annotations, and at least 3 annotations per image. Lacking manual expert annotations, we use the staple algorithm calculating all given annotations for dataset A, assuming this as a ground truth to be tested again. We need no ground truth for B, but we get there in a moment. While speaking of quality of our datasets and annotations, it is important to mention that we define quality as compliance to ground truth. The upside of this is we can simulate different levels of quality by using a different amount of user annotations to generate our annotations for training the neural networks. Grounded on previous work and the fact that we want reasonable differences between our training data, we use the worst annotations first in calculating the training annotations. This is referred as ascending order. This results in 8 different quality levels for training the models related to the first research question. You can see our split sizes slightly differing from the usual splits because of our small dataset A. Please keep in mind that our assumed ground truth includes 15 images with staple masks using all given user annotations. For the second research question, we varied the size of training and validation sets to investigate the influence of dataset size by a given quality level. We have 2 quality levels of annotations using 1 or 3 annotations per image, calculating the training annotations. Because of the nature of the research question, we have differing split sizes with a not constant ratio. To compare models of RQA and RQB, we decided to use the same test set of images for all models. In particular, 15 images from dataset A with high quality annotations. During our work, we trained 60 models for RQA and 28 models for RQB, using an already implemented version of the UNet by Jakubowski with VGG 16 pre-trained models. To compare those models, we use the F-score as error metric. As expected, we saw an increase in segmentation performance for models using higher quality annotations, but with just small improvements above 15 annotations per image. While we see a logarithmic improvement for models of RQB using more images for training, additionally we observe a rise in performance when using higher quality annotations. Though there is no direct dependence of number of images or quality level alone. In consequence of that, we looked at the number of used user annotations. While we see that the best and the worst result are performed by models using the most and the least annotations, there's still room for improvement in between. Models using higher quality are easily outperformed by models using more images, but also we can see that at the example of a model using 900 images and 1 annotation per image, and another model using 300 images and 3 annotations per image, the latter performs better. So, regarding of our findings so far, we recommend collecting at least 3 annotations per image to reduce ambiguity and achieve a minimum level of annotations quality, assuming untrained users. While we trained the models for RQA, we trained another 2 models without the use of stable. We fed the user annotations directly into the neural network, respecting the previous splits. Therefore, the number of annotations is the same, and To our surprise, the performance is on the same level as well. That was a starting point to another experiment. We trained 6 staple and no staple models on the second dataset and tested them on our entire dataset A with highest quality annotations as ground truths. As a result, we got similar performance, resulting in an F-score difference of just 0.1% averaged over the models. Our work is limited though, due to small datasets, a specific use case, and just a small emphasis on optimization. Furthermore, we conducted that 2 models per configuration are not enough to identify outliers reliably. In conclusion, we saw that the distribution of annotations on different images quickly outperforms higher quality of annotations per image. A certain level of annotation quality should be assured as well. In our case, a reasonable upper bound were 15 annotations per image. In our work, we concluded that training a CNN with higher quality annotations increases the segmentation performance, but distributing annotations over as many images as possible is more efficient in the long run. A minimum of at least 3 annotations per image is nevertheless advisable to reduce ambiguity, and staple as an additional aggregation layer may be unnecessary, and we propose to review the step in the future and use the user annotations directly for the training of the neural networks. We look forward if our results can be validated in other applications with larger images, datasets, and other segmentation tasks in fields like histology. Thank you very much for your attention. I hope you enjoy the digital conference and have a nice day. Goodbye.
Hi, my name is Nicolas Spicher and I welcome you to this talk. I'm a postdoc at the Peter L. Weichert's Institute for Medical Informatics of the TU Braunschweig and Hannover Medical School, and in this talk I will give you information on a gamification concept that has been developed by one of our PhD students. As many of you will know, the segmentation of images is a typical task in medical image processing applications. Recently, deep learning methods, such as convolutional neural networks, have been shown to outperform classical methods like pixel or texture-based algorithms. However, these methods rely on a large number of training data, and these training data are costly to acquire. In this work, we therefore present a cheap method to acquire training data using gamification. Our use case here is the segmentation of the sclera of the eye, and therefore it is a typical binary classification task with 2 classes, representing the sclera and representing everything else. In the following, I will use the term annotation mask for the binary image that delineates the sclera. So we have some experience in this field, and in last year's conference we analyzed the characteristics of training data for an optimal CNN training. We analyzed the results of 44 users that were provided 75 images of the human eye for segmentation of the sclera. On the right you can see the provided results, so each column represents a user and each row represents a provided image. A green box indicates that an annotation mask has been provided, while a white box indicates that no mask has been provided by the user. We took this as starting ground for analysis, and we analyzed these annotation masks, and we derived 4 requirements for an optimal CNN training. The first is that the quality of annotation should be maximized. This is self-evident, but we give it here for the sake of completeness. Furthermore, we observed that for each image there should be at least 3 annotation masks. Additionally, the number of images with annotation should be maximized to have a dataset with a high variability. And furthermore, we observed that there is a learning effect, which means that the annotation masks provided by long-time users have a higher quality than the annotation masks provided by new users. Therefore, in this work, we propose a concept which aims for fulfilling these requirements by the means of crowdsourcing, or to be more precise, by gamification. From literature, we know that there are different types of crowdsourcing and motivations of the crowd. The first type is citizen science, and there the users are motivated by helping to progress the scientific research. The second type are microtasks, and users are motivated by payments that they receive. The third types are games with a purpose, where users are motivated by personal entertainment only. And in this work, we focus on games with a purpose. There are different types of incentives which are typically used. You all will know, for example, scores, leaderboards, achievements, or a level system. Therefore, the research question of this work is how to design a game with a purpose for sclera segmentation, which makes use of these incentives and also fulfills the requirements shown on the previous slide. Here we propose the game concept of Dr. Columbus, which is inspired by the popular web game Paper.io. Each player controls a ship that sails on the sclera. The ship has a trail, which indicates its traveled route, and outside the sclera, the trail turns to red. When returning to a visited area, the player increases its size. Therefore, the overall aim of the game is to cover as much as possible of the sclera. But unfortunately, there are other players as well, and outside your area you can get destroyed. Therefore, the game mode is Last Ship Sailing until only one ship is left. This concept provides an intuitive mapping of the tedious segmentation task to a fun game. However, we have no information on the quality of the provided segmentations. Here you can see another example of a user increasing its segmentation mask. However, quality has to be ensured such that the data can be used for CNN training. Therefore, we introduced scoring mechanisms. There is a quality score which is invisible to the player and measures how good his or her segmentation fits to the ground truth. Additionally, there is an effort score which is also invisible to a player. But as you can see, it increases with each game round independent of the player's performance. Finally, there is the overall user score which is shown to the user. It combines the quality score and the effort score. The user score can be used now for different incentives, fulfilling the requirements shown before. Here we analyze in how far this game concept fulfills the requirements. So the scoring, for example, is used for short-time motivation and therefore fulfills the first three requirements, as we hope to motivate the users to play just one more level. Here you can see the in-game high score list, which is shown during playing and represents the user score U. Furthermore, we have a level system, which is updated after each game. The user scores are stacked and are kept forever. By this, we hope to maintain long-time motivation and thereby fulfilling requirement number 3. Additionally, we have in the menu a leaderboard, which shows the best Columbus of the day, week or month, which is somehow between short and long-time motivation. It allows the new users to gain fast achievements, for example by becoming the Columbus of the day, but also motivates the more long-time players. Finally, the quality score is not directly used within the game, but we use it to assign a trustworthiness to the obtained annotation masks. So let me now give some technical details. The game is a typical client-server application, and the clients are being developed in Unity, which is a popular framework for game development, and the server is developed as a Node.js server. So what we did is we outsourced the image database from the game server such that it can be easily replaced by other servers or image types. And here in this work, the images are provided by the relineation platform we proposed at last year's conference. A typical gaming sequence has 3 steps. At first, the clients acquire the images from the relineation platform. Then the server initiates the game and interchanges the data between the clients, and after the game is over, the generated annotation masks and quality scores are transferred to the relineation platform. Of course, this is completely transparent to the user, and now I want to show you a short demo. So this is the starting screen, and now you can see we're in the main menu, and you can define a name and alias for your user account. And here then we have the typical elements of a game. You have a personal account, you can change your name or upload a picture such that other players recognize you. And if you click on multiplayer game, you can see we have here a list of servers. At the moment it's only one server and you can join it. And then you can decide where to start. And then the game starts. So here you can see this ship is currently controlled by the player. You can control it with the mouse or with the key arrows. And when you return to the area you already visited, it gets larger and larger. When you leave the sclera, your trail is red. So we hope to motivate the user to not leave the sclera, and they also can get minus points. On the right bottom, you can see there is a minimap, so you can see where exactly you are at the moment. So let me now discuss here the results a bit. So as we described, acquiring image annotation masks is a tedious and a costly task. In this work, we proposed the game with a purpose, Dr. Columbus, for the gamification of this task. The game fulfills the requirements for optimal CNN training that we derived in early work, and we provided different incentives. Furthermore, for each annotation mask there is a score that we will now use to assign a trustworthiness to each obtained annotation mask. In future work, we will evaluate the influence of incentives on the quantity and quality of the obtained data, and furthermore, we will compare this gamification approach to other approaches like citizen science or micro-task-based crowdsourcing motivated by payment. This concludes our talk. Thank you for your time.